Hello. We're going to take a look at DeMoivre's theorem today, which is basically a general rule for raising any complex number to a power. After we get Euler's formula, we won't really need to rely on DeMoivre's theorem as much because we can go back to our, we'll be able to just use exponent rules for it. But DeMoivre's theorem follows really nicely from our results of multiplying numbers in polar form. So I'm going to first state what DeMoivre's theorem is, and I'll try to show you an explanation for why it's true after that. So we'll start off by defining z as a complex number in polar form. So let z be a complex number where such that z equals some distance times cosine plus I sine theta. Cos theta plus I sine theta. This is just the polar form for z. Then DeMoivre's theorem says, if we raise z to a power, z to any power, any integer power actually, it was proved. Later on it was proved that it works for any number. It doesn't have to be an integer, but let's just pretend z is an integer for now. Or n is an integer, excuse me, that this power is an integer. Then if we raise it to a power n, we get r to the n, and then cosine of n times theta plus I sine n times theta. So if we look at what the impact raising the complex number to a power is it says raise the distance to that power, multiply the angle by that power. So really what's going on here is that this is multiply r by itself n times. Because that's what exponentiation is. We're saying multiply z by itself n times. So we're going to have z times z times z, a bunch of z's, n of them. And so there's going to be n r's multiplying each other. So we're going to have r times r times r times r. And that's a shorthand way of saying shorthand way is r to the n power. And then for this one, we're really just doing repeated addition. Add theta to itself n times. We're adding theta, and we're adding theta, we're adding theta, and theta, and theta, and theta. And this part comes from the fact that when you multiply two complex numbers together, you multiply their r's and you add their angles. But we're just doing that n times. That's all we're doing. So I'm going to try to justify that using the multiplying rule. So there's DeMoivre's theorem in all its glory. Z to the n equals r to the n cosine n theta plus I sine n theta. Okay, so where does it come from? Well, I'll try to write it out. So let's look at z. So we'll start off with what z is. That's r cosine theta plus I sine theta. And then let's look at z squared. Well, this is r cos theta plus I sine theta. Times another r cos theta plus I sine theta. It's z times itself. So we can group this, like we can group the r's together because there's an r here and an r here. We can multiply in any order. So let's group the r's together. That's going to give us r times r in front. And now we have to do the distributive property, but we already know what the result will be when we multiply these parts. Because we did this before, is that we end up getting this long identity for cosine and another identity for sine, which just ultimately means we add the angles together. So we end up getting cosine of theta plus theta, right? And for the other one, we're going to get I sine of theta plus theta. Right there. And what does this boil down to? Well, this is r squared cosine of 2 theta plus I sine of 2 theta. Seems to work for z squared. Well, what happens if we add on another z? So let's look at z cubed. Well, now this is z squared times z. And I already know what z squared is. That's r squared cosine 2 theta plus I sine 2 theta. Because we found it just a minute ago. And I just multiply this by another r cos theta plus I sine theta. Let's see, that's showing up. Yeah, there we go. So I multiply it by z again. I'll just do a little bit of color coding so we keep track. Z squared is this guy, and z is this guy right here. So let's do some grouping again. What makes the most sense for grouping? If we group the r's together first, again, we write all the r's in front. R times r squared, that's going to give me r cubed. And now let's do the foiling. Well, we don't need a FOIL because we already know what's going to happen when we do that. We just add the angles together. That's the result we had earlier. So we do 2 theta and theta. So we're going to have cosine of 2 theta plus I sine 2 theta plus theta. And we know what this is. That's 3 theta. That's 3 theta. So we get r cubed cosine 3 theta plus I sine 3 theta. And that's z cubed. And as you can see, we keep going on and on if we want to, but we see the pattern that's emerging is that when we square z, we get r squared cosine 2 theta plus I sine 2 theta. When we cube it, the r is cubed, and the theta is multiplied by 3. It's just repeated multiplication. That's what exponentiation is. And so we just multiply the distances by itself that number of times, and add the angles by themselves that number of times. That's DeMoivre's theorem. We'll do an example next.